morning, everyone. Welcome to the first Australian Deep Carbon Observatory workshop. This particular workshop is mostly designed towards modeling deep carbon in a tectonic and geodynamic framework, but we will actually cover many different timescales in the various talks. And of course, the more recent timescales and processes that have occurred there inform our understanding of what might have been happening in deeper geological time. So deep time is really what motivated the Deep Carbon Observatory. It's perhaps the greatest single contribution of geology to our understanding of the history of planet Earth. It's the concept of deep time, or geological time. It's the kind of thing that most humans have a hard time grasping, because we are mostly concerned about the timescales that humans experience during their lifetime. But combining deep time, geological time, with the concept of biological evolution, well, that's led to a scientific explanation for the biosphere as part of the natural history of the Earth as it has taken shape. And so these two fundamental concepts are inextricably linked because an awareness of deep time is in fact a necessary requirement for understanding the long course of biological evolution of life on Earth. And I think it would be fair to say that ultimately this is really what the Deep Carbon Observatory is all about. So the DCO is a global research program that's designed to transform our understanding of carbon's role in the Earth system. It's a community of scientists that includes quite a variety of different subject areas, including biology, physics, geoscience, chemistry, and the DCO is particularly designed to facilitate work across these traditional disciplinary boundaries and to develop new integrative carbon science. And so we are hoping to make a small step towards that in this workshop. Some of you might not be too familiar with the DCO. So it's led by Robert Hazen, and it was launched in August 2009. Its secretariat is based at the Geophysical Laboratory at the Carnegie Institution of Washington, D.C. The DCO's research is very much focused on the carbon cycle beyond the Earth's surface. And so DCO looks at high pressure and extreme temperature organic synthesis, complex interactions between organic molecules and minerals. They conduct field observations, and they look at theoretical models of how the lower crust and the upper mantle and carbon sources of sinks might have developed through time. And so if we take a step back, then the Deep Carbon Observatory is really designed around four themes or science communities. So that's reservoirs and fluxes, deep life, deep energy, and extreme physics and chemistry. Now, this workshop and our own activities are mostly, for the moment, focused on reservoirs and fluxes. And so this reservoir and flux community of the DCO explores the storage and transport of carbon in the Earth's deep interior, and of course, how it's connected to the shallow Earth, to the hydrosphere and atmosphere, and to the biosphere, ultimately. Now, because we have plate tectonics on Earth, so that sets the Earth apart from other planets in the solar system, at least at present day. And so the creation and subduction of tectonic plates, they involve all sorts of processes that influence the deep carbon cycle. So that includes volcanic outgassing, for example, at mid-ocean ridges, also at subduction zones. So it's these sorts of processes that we're trying to understand through deep time and how they vary. And so they remain quite poorly understood. And of course, we cannot directly sample processes in deep time. So we have to use proxies and simulations and models to better understand how the Earth might have evolved around its carbon cycle. So the goals of our own workshop here today are to bring together climate and geoscientists from around Sydney, national and international collaborators, and this is based on a DCO-funded deep carbon modeling project. It was a relatively small sort of pilot project, But I think it would be fair to say that we've actually managed to do a fair bit of work as part of this. And so this workshop was part of our funded project. So we'll try to communicate what we've done so far to you, and on the other hand, all those of you who were not directly involved in this project can make a contribution by talking about your work on the carbon cycle and how this may perhaps lead to future collaborations and connecting different timescales to each other. So we want to explore the interplays between the atmosphere, oceans, crust, and mantle in the deep carbon cycle on a variety of timescales. So we have developed some modeling tools for conceptualizing and visualizing carbon cycle-related data in new innovative ways in deep time. Of course, this involves G-plates and pi-D-plate softwares that allow us to attach data to plates, plate boundaries, and understand how tectonic cycles have driven parts of the deep carbon cycle. And particularly on the second day, we will then get to discussing outstanding problems and have a bit of a brainstorming session to develop some ideas for future projects and new funding mechanisms to support this fledgling research area. That's the end of my introduction. Are there any comments or questions at this point? So if there aren't, then we will move right on to our first talk by Sabin Zahirovic, who is also happy to have his presentation streamed to the rest of the world.
That's right. So this is the experimental first iteration of EarthByte streaming to the world. Okay. Don't forget your coffee.
Oh, my coffee cup, yeah. Thank you.
Okay, good morning everyone. Nice to see you all. Thank you so much for coming out today. Many of you are external visitors, so it's great to see all of you today. As Dietmar mentioned, we are live streaming this, so if you tell us before your talk if you're not comfortable with that, that's cool, we'll just pause that. As some of you know, my name is Sabin Zahirovic. I'm a postdoc here at Sydney Uni, and today I'll just introduce some aspects of these emerging technologies in modeling deep carbon. I'd like to actually provide more of a background for Jody and other speakers that was based on our DCO project that Dietmar mentioned. So as Dietmar said, the Deep Carbon Observatory is a 10-year project, started in 2009. Bob was very proud to say it's amassed about $1 billion in funding, which is great. It engages more than 1,000 researchers in more than 50 countries, and there are some specialty groups within that. And the idea of deep carbon is that at least 90% of carbon is thought to be inside the deep earth, in the mantle and in the core. And so the deep carbon community studies the interaction and the exchanges from the deep reservoirs to the shallow and surface reservoirs, the interaction of the biosphere and the geosphere. So, as part of our EarthByte activities, we consider both the deep Earth at present day, but we include this temporal component of deep time, geological time carbon cycle. And we recognize the importance of plate tectonics in driving these exchanges of carbon between deep Earth and surface environments and shaping climate and evolution as well. So many of you have seen this schematic from some of the promotional material, but it describes this deep carbon cycle that operates at greater spatial scales than some of the more shallow carbon cycle that we're used to studying at school and so on. But essentially, most of you would be familiar with the idea at seafloor spreading centers that we have oceanic crust production and degassing, so a lot of CO2 coming out from the mantle, but actually very quickly through hydrothermal alteration, you capture a lot of CO2 into the upper crust. As the crust approaches the subduction zone, it ages and accumulates lots of sediment. Much of that will collect carbonate-rich material, which enters the subduction zone, and some of it will come out as CO2 from arc volcanoes. Some of it will be entrained in mantle convection, so the carbon is easier to entrain in mantle convection than water, because carbon can form many accessory minerals that are stable at depth. And so this gives you an idea, and the ranges of numbers are just the estimates. It's very difficult to measure and measure each aspect of the deep carbon cycle. So my involvement in all of this started in 2015, so last year, when I attended the DCO modeling visualization workshop in Washington, D.C. And it was a collection of interdisciplinary researchers who needed a platform, a software that was community-driven and could help with their modeling, their visualization, and outreach. And so there's me in the background there. Maybe you'll see me. I need to get a different pointer because, yeah, there's me. Okay, so it's a miracle that we managed to do any science or discussions because we were in the Smithsonian Natural History Museum amongst these beautiful specimens. But the main purpose of that meeting was to talk about this transition of the DCO from being the first 5 years of collecting data to the second years of focusing on modeling. And so there were a number of other partners, software partners, many proprietary, such as ArcGIS, MATLAB, that were there. But through the discussions, G-Plates became the favored platform for doing some of this modeling, visualization, and outreach for the DCO. As Dietmar mentioned, out of that activity, we were funded a program called Spatio-Temporal Modeling of Deep Time Atmospheric Carbon Flights from Subduction Zone Interactions with Carbonate Platforms. All that really means is that we were looking at regions where we have a subduction zone with arc magmatism that may be interacting with buried or active carbonate platforms, leading to decarbonation and emission of CO2. Now, we actually didn't focus on the present day. We focused on the plate reconstructions, paleogeographic aspects of it. So Jody will talk about this in more detail afterwards. But with that money, we were able to hire two very talented research assistants, Jody and Sam, who will talk today and tomorrow. And we've been collaborating with Kyra Matthews at Oxford, Louis Morazi at Uni of Melbourne, Mike Ernest at Caltech, and Adrian Milnardi at Rice University. And so at present day, if we just look at this map, it's just topography. And from the Global Volcanism Program, you see all the yellow triangles are Holocene volcanoes that are not subduction related. And in purple, you see these subduction related arc volcanics. In very bright green are active or recent carbonate platforms, such as reefs. And then in this light green, which might be a bit hard to see, is buried or inactive carbonate platforms from the paleogeographic reconstructions from Kiesling et al. 2003. So I'm not going to go into too much detail because Jody will cover many aspects of this. So there's a few external visitors here who might not be too familiar with G-Plates, which is the community-based, open source, and cross-platform software that we develop here. It's a deep time GIS platform, essentially. And of course, we use it with plate tectonic reconstructions. Others also look at paleobiology, ocean circulation, climate data mining. And we'll also be looking at geodynamics, paleogeography aspects of the deep carbon cycle. So how do we actually do the plate reconstructions? So here is the seafloor age grid from Dietmar. And what we can do from the seafloor, we can just figure out the age of the seafloor and undo that seafloor spreading and figure out the arrangement of the continents. We can supplement that with the continental record as well. but that allows us to create true plate tectonic reconstructions. And one of the biggest advances was when we implemented an algorithm in G-plates that creates evolving plate topologies. So a user can digitize individual plate boundaries. They can all move independently of one another. The G-plates will close that topology on the fly. So we can create evolving plate topologies in, say, 1 million intervals, where we can, for this project, we were really interested in the length of subduction zones through time. And the key assumption there is that, well, if we have more subduction zones, you'd think that perhaps you have more arc volcanism and CO2 outgassing. And so that was one assumption. So any perturbation to this deep carbon cycle might then manifest itself in the CO2 proxy record. That was an idea that we explored. So this is what the resulting models look like. We have Pangea breakup happening here, and what you'll see are black lines that represent mid-ocean ridges and transforms, and these pink lines which represent the subduction zones. And as you can see, we have a complete topology of plates in 1 million year intervals. We can extract plate velocities, subduction zone lengths, and characteristics from there. So this was work we did in the last couple of years, and this was using our older plate reconstruction from 2012. And so for that plate reconstruction, I extracted the subduction zone lengths in 1 million year intervals, and I did this painstakingly. I wouldn't say manually, but I had to do it in ArcGIS one time step at a time. Okay, so 200 times. And but anyway, I was able to extract these subduction zone lengths from the model, which we interpreted in different ways for that study. But in the context of this study, what you can see here in red is the subduction zone lengths from that model, and in black are the subduction zones from our very recent plate reconstructions, so the 2016 plate reconstructions, which represent about 4 years of effort of increasing detail in key regions like the Arctic, Southeast Asia, the Tethys, and the Pacific. And what you can see, many of the trends are still there, but we actually have more subduction zones that we're documenting and capturing. So that's interesting. And this is a very tiny graph. You can't probably see very much from a distance. This is the oxygen isotope curve from Zahos et al. 2008. And they had a peak at about 50 million years ago, which corresponds to a peak in our subduction zone lengths, presenting very warm climates in the Eocene. Now, clearly, the subduction zone lengths are not the only thing controlling climate and temperature, but we think that it's an important thing to evaluate and look into. When we think about the long-term cooling of the planet, many factors come into play, but one of the things seems to be the India-Eurasia collision has been implicated in this, with silicate weathering taking CO2 from the atmosphere. And we also have a decreasing length in subduction zones. So this is the concept that as you have CO2 degassing, you have lots of CO2 in the atmosphere, but when you have mountain building, such as the uplift of Tibet and the Himalayas, you accelerate silicate weathering, chemical weathering that sequesters CO2 out of the atmosphere. And it's thought to have contributed to the long-term cooling of the planet. So this was recently modeled and explored by Yaguts et al., who looked at the India-Eurasia collision. Here is 80 million years ago on the left, 50 million years ago on the right, and we have a two-stage collision. So first, India collides with an intra-oceanic arc, and then we have the continent-continent collision. And the key point here is that Greater India collides with the intra-oceanic arc. We have ophiolite abduction and orogenesis, Okay, lots of silicate rocks being exposed to the atmosphere in the equatorial band at very high rates of silicate weathering. And you have that two-stage collision. So when they modeled the balance between the output of CO2 from arc volcanism, this is what we have in the red here. There's a little bump around 60 million years ago. And this is the curve of the consumption rate from silicate weathering. When they combine those two things, they get this red curve here through time. Okay, that's the Cretaceous, 100 million years to present. And in the background, in the blue, is the deep water temperature from the proxy record. So they argue that they can reproduce at least some of these trends, and I think that's quite an interesting study. However, because they just look at that collision zone, they ignore all the other subduction zones and everything else that's going on in the world. We have an opportunity here, because we've got these global reconstructions, to do something similar globally. You can see there's a huge discrepancy here in the younger times because there's complexity in Southeast Asia and all these other parts of the world. In the plate reconstructions, they're very information rich. We can extract seafloor spreading rates that you see here in the animation below. That's been used in the past to look at hydrothermal fluid flux, ocean chemistry, but it's never really been used to look at the carbon content of the crust. So Dietmar will talk more about this later today, but from ODP and DSDP sites, the drilled basalt, the basement, indicates that with increasing age of that crust, there tends to be more CO2 or carbon trapped in that basalt. And it seems to be from hydrothermal alteration and other aspects as the crust ages. So what we can do is turn that relationship and apply it to our seafloor age grid through time, and we can have we can create these dynamic grids through time that we can potentially then feed into geodynamic models such as sitcom-S models. So Mike Gerner suggested that such an approach in the future. So that's something interesting to keep in mind. Okay. In the future, we hope to collaborate with other experts in using box models of carbon cycling because we don't have that expertise here, so that'll be very interesting to incorporate some of these measures of subduction zone lengths, mid-ocean ridge lengths, spreading rates, and subduction zone fluxes. In terms of the geodynamics, well, we've already got quite advanced geodynamic models, 3D spherical through geological time, and Mike Gernes was quite keen at exploring, feeding some passive traces into the subduction zones that represent some of this carbon content, and seeing whether you might have regions of the mantle that are more enriched or more depleted in some of this. Now, it's very complex to actually have the realistic carbon physics. I don't think we'll be able to do that, but it's worth exploring as well. Over the summer, we have 2 summer scholarship projects. One of them will be looking at large igneous provinces. So one of the famous examples is the Cretaceous Ontong Java Manahiki Hikurangi super large igneous province eruption, and that seems to have contributed to Cretaceous greenhouse. We'll be looking at continental large igneous provinces, say it's just Siberian flood volcanics, and other continental flood basalts, in terms of, well, they inject a large amount of CO2. Often the Siberian traps are famous for actually releasing a lot of CO2 that was trapped in limestones and coal. So we'll be looking into how it releases CO2, but also the weathering of those lit products as they move through the different equatorial climatic bands. So that's going to be interesting. And we'll be looking, and the other project, we'll be looking at slab flux through time. So previous studies have looked at seismic tomography, so images of the mantle structure, and interpreting these blue blobs to represent subduction zones. This is one interpretation. There's many subduction zones here, but this is just based on snapshots. It's very difficult to create continuous plate motion models from such reconstructions. But anyway, they could estimate the slab flux from such interpretation and convert that to atmospheric CO2 emissions. So we can do something probably more detailed based on our plate reconstruction time temporal resolution. Just a couple of months ago, there was a paper published in GCube by Lee et al. And they used the 2012 plate reconstructions that I briefly showed, and they coupled it to a mantle convection code, and they estimated melt production, so that's here in grey through time, so there's 200 million years, Pangea to present, and from that they could also estimate the degassing rate of CO2 through time. So they found that between around 150 to 120 million years ago, there was a huge spike or huge acceleration of degassing, and that could be linked to this the greenhouse conditions in the Cretaceous. So that's something that would be very interesting to explore with the updated plate reconstructions. Louis is probably the expert here, so we'll have to discuss that with Louis and Mike. Okay, and then so that's the summer scholarship projects, some of them that I mentioned. Jody has kindly indicated that she might be interested in honours next year. From these two summer scholarship projects, there's been unprecedented amount of interest from students, so we hope that some of those students will also be interested in deep carbon observatory related work. More longer term, we have an EarthLife Database, and if we know the age of abduction of those EarthLights, we can link them to the plate reconstructions and look at those weathering rates as well as they pass through the different latitudes. So that's global, and that'll be quite interesting. And as I mentioned, the geodynamic modeling with trace stress simulation will be very interesting to explore in the future. Okay, so in conclusion, I hope that you can see where this workshop is heading in terms of highlighting the fundamental role of plate tectonics in the deep carbon cycle that has implications for a deep time climate, sea level, ocean circulation, extinction, and so on. One of the key things here is that we are trying to build open source community software and workflows to tackle such a complex and interdisciplinary problem. So we hope to do that with G-plates, Pi-G-plates, and Jody and Sam will talk more about that. So I'd like to acknowledge all of these people. Thank you very much, and I'll open up for questions. Thank you. Dietmar.
I actually have a short comment, not a question. There is in fact a third summer scholarship project that is also perhaps indirectly DCO related, which is designed to improve our knowledge of Cretaceous sea level variations. And of course, I just thought I'd mention that briefly. And we have had in fact a number of applicants for that project as well.
Right.
Because long-term sea level is also known to be an important driver for certain aspects of the carbon cycle, because as you flood continental shelves and parts of the shallow portions of the continents, especially at low latitudes, because they become areas where carbonate is being deposited and carbon is being sequestered out of the system. And whereas as you lower sea level, first of all, you lose part of that sink, and you also start eroding these rocks. So yeah, there's definitely a connection between that project DCO as well.
Fantastic.
So Jody, that was really interesting. The using the subduction lengths to get at how much the carbonate platforms contributing to that. Are you able to estimate the volume of the carbonate platforms, or do you just take the length as the proxy, or how do you are you trying to look at that? I guess so the amount of carbonate.
Yeah. So that's a great question. I'm glad you asked me that. There are a few key things that we can't really do that well. One of them is figuring out the detailed sedimentation and the amount of carbon in the downgoing sediments. In terms of the carbonate platforms on the continents, in the overriding plate, that's also difficult to estimate the thicknesses. So these are carbonate platforms that are mapped, say, and interpreted from seismic. So they've been linked to these paleogeographic reconstructions. One thing that we can't do is figure out exactly when they were active, how large, extensive they were, and thicknesses are probably the biggest uncertainties. So what we do is we just look at we have a long subduction zone, and we have a blob that represents a carbonate platform. We just figure out what percentage of that subduction zone may be interacting with a carbonate platform. The other difficulty here is that slab dips. Okay, that's difficult to figure out at present day, and that controls where your arc volcanism will actually be erupting. So you could completely miss your carbonate platform or go right through it. The way we looked at that, we looked at the present day distances between the subduction zone and arc volcanism on average, and we had a buffer, so we applied that to the carbonate platforms in deep time. And Jody and Sam will talk more about that.
Do you have a sense of whether that underestimates or overestimates, or the amount of calcium carbonate going down? You just don't know.
I'm not sure. I think some of it might be underestimation because of erosion that this may actually destroy old carbonate platforms, say through mountain building and so on. So they tend to be more well mapped, say on passive margins, than say in mountain regions. Jill?
Yeah, I was wondering when the model the effects of mountain building on silica weathering.
Yeah.
Do they incorporate the effect of metamorphism in CO2 degassing? Just for the Himalayas, for example, you've got all this hidden platform which gets incorporated, and you have recently they made a pretty large process of diffuse CO2 coming from the mountain range. So do they actually compensate for this effect?
I don't think so. I think they're just looking at the chemical weathering of the silicate rocks rather than the metamorphism, which, like you say, is an important aspect of this cycle. Yeah. So there are many boxes, many aspects of the cycle, and the carbon cycle. That's something we're kind of grappling with as well. Like we look at the tectonic part of it, but there are so many other things. There's the biosphere as well, and other very large, significant contributors. Yeah, that's very good to keep in mind for us. Okay. That's it. Is it morning tea? Oh no, it's Jody.
It's
Yeah,
Jody, of course.
But get up and like stretch your legs, like there's some chai green tea here, and we have some live set up.
Okay.
Just eating it.
Jody, have you got
I
your
think USB.
I'm just going to pause this live streaming.
Yeah, sure.
Goodbye, world.
The graduate student here and has taken the DCO project here as an opportunity to become involved in research before her honors project. And I think it would be fair to say that he was fully convinced that she's done quite a bit of work as part of this project. And so over to you, Jody.
Thanks. So I'm just trying to get it so it takes up the whole screen. but it doesn't want to do that, but that's okay. So firstly, I'd just like to acknowledge that we're meeting on the Gadigal people of the Eora Nation. Sovereignty is never ceded, and I want to pay my respects to elders past and present. So yeah, like Deepa was saying, this year I've had the immense pleasure of being able to work with himself and Sabine and Sam on this deep carbon modelling project, which was funded by the Deep Carbon Observatory. And one of our objectives was to visualise the configurations of subduction zones since the Devonian, and to make a tool to quantify subduction flux through time. We know so little about how tectonics has influenced Earth's paleoclimate, so part of our job was to be able to fill in some of those knowledge gaps to see how some aspects of the deep carbon cycle interact with each other. So the tool is basically a first approximation of how CO2 emissions and volcanic arcs have influenced the climate in deep time. We use subduction zone lengths as a surrogate for carbon dioxide flux at subduction zones. In the presentation, I'll just explain a bit about why the tools are useful, some of the processes that we went through, and then I'll go through some preliminary results. Bear in mind that we are yet to deeply unpack the results we've obtained, because we only just finished modelling a month or so ago. So we can unpack these results in more detail tomorrow. But yeah, we've created a tool that tests a whole range of hypotheses about plate kinematics. So yeah, keep in mind the potential for this tool. So Sabine attended a deep carbon visualization and modelling workshop last year, and two of the takeout lessons were firstly that there would be no model that can serve both research and public communities, and that the number one barrier to creating a carbon model is the lack of basic data and theories. It might be bold in saying, but I feel like we've kind of tackled both of these with our G-plates models, because we were able to create like a first approximation of how CO2 flux or carbon dioxide flux at subduction zones influences climate, and the tools we have, we've created a whole bunch of outreach products that make it interactive with both the general interested community and for researchers to be able to test hypotheses. We had two objectives. Deepa is going to talk about the second one tomorrow, about the amount of carbon removed in reservoirs through subduction of the ocean crust. But what I will be talking about is the influence of subduction zones on arc volcanism and the carbon dioxide emissions through time. We did that through using the surrogate of subduction zone lengths. We're trying to estimate the extent to which arc volcanisms interact with the carbon crust to liberate more carbon dioxide, and then quantify whether the subduction zone lengths were overall in a continental arc regime or an island arc regime. So you've seen this schematic before. This was in Sabine's presentation. Basically, the big takeaway is that the deep carbon cycle operates on million-year timescales, and that arc volcanism and ridge volcanism produces about 90% of the carbon dioxide into the atmosphere on a yearly basis. We don't know very well the mechanisms of transferring carbon from the mantle into the atmosphere, but that's not really the scope of the project. We were mainly just using the lengths of subduction zones to see how they've changed through time, and using that as like a surrogate indicator for carbon dioxide emissions at arc volcanoes. So what do we know about the Cretaceous springhouse? Well, the baseline climate had elevations of atmospheric carbon dioxide that were 4 to 8 times present day levels. After the opening of the Atlantic, there was a period of enhanced continental arc activity, and you can see that in the first graph, and that corresponded to rising surface temperatures, sea level surface temperatures. As well, subduction zones were really high because of the dispersal of continents and the faster mid-ocean ridge spreading rates. When Vandermeer and others put that into a climate model, they saw in the second graph that it actually corresponds really well to the proxy record, which is the grey envelope, and their results were the blue line with the error bars. It's we're not quite sure what caused the the increase in atmospheric CO2. Like it was most likely a combination of factors, but perhaps it was the length of the subduction zones or the change in the nature of subduction zones that caused this large CO2 emissions and like the climate that prevailed. So that's kind of what we wanted to test as well. Just basically continental arcs, are built through continental crust. If there are deep, thick mid-crustal carbonates buried, they'll the magma will interact with that and liberate vast amounts of carbon dioxide. This simply doesn't really happen with an island arc-dominated regime because there aren't thick layers of carbonate, so less CO2 emissions are really liberated there. So the implication is that if continental arcs dominate, we're going to see a significant release in carbon dioxide into the atmosphere, which occurred during Cretaceous. Just a word of what I mean when I say carbonate platforms. The proliferation of shallow water carbonates during most of the Phanerozoic has led to a buildup of carbonate reservoirs on the shells of continents, and they're huge stores of organic carbon. They don't form in the deep ocean, and that's why you don't see island arcs intersecting with carbonates, broadly. So the literature essentially suggests there's a causal link between carbon dioxide reduction and the intersection of arc volcanoes with carbonate platforms. So this is a bit about how we created the model. So we reconstructed the distribution of carbonate platforms from Kiesling's paper. So this is, his figures, and then we geo-referenced them using ArcGIS to create a static map of the carbonate platform distribution. And then after that, we were able to assign plate IDs to the carbonate platforms so that they would be able to move with the model. We did that by a process of cookie cutting. So basically you create a polygon, you can see this in the picture, you create a polygon that crops a feature of interest and then assigns everything within that region to the plate that it's overlapping, and in that way it can rotate through time with the plate kinematic model that we have. So our understanding of plate kinematics has improved since this map was made by Kiesling. We used an old model, likely the one that Kiesling used, to be able to first assign plate IDs. Then we had to reassign a new plate model to represent our current understanding of how plates have moved through time. So we reassigned plate IDs based on the Matthews plate model, which is the one that that has been currently developed by EarthByte members. And then after the reconstruction, we just tested how the subduction zones interacted with carbonate platforms since the Devonian, so 400 NA. There was a problem about, I think Jody raised this, how long do carbonate platforms interact with volcanic arcs? I don't know if this setting will work. Oh, sorry. I'll have to maybe show you later. But there were two models that we really looked at based on whether carbonate platforms are this model here, whether they accumulate through time, so they build up and they get thicker and thicker, or whether they, that's actually sorry, I've switched them around. This is the active carbonate, the accumulated carbonate model. The active carbonate platform evolution is based on the idea that they, decarbonation processes are really efficient, so it kind of consumes all of the carbonate reservoirs and releases that, there you go. Yeah, so they end up depleting through time, and so the spatial distribution is always changing. So these were the two primary models that we looked at, an accumulation model or an active development model, assuming that decarbonation is very efficient. Look, we didn't really know which one was dominating either. We're not sure if this is more likely or this is more likely. In reality, it's a mixture of both, so we do need to refine our model of carbonate platform evolution. But, as a first approximation, it was pretty good. We did get some good results. Does anybody have any questions about this, about how they're different? Okay, good. Okay, so what did we do? Sam and I created a series of scripts which communicated with G-plates through the Python PyGplates programming language. We basically extracted all subduction zone lengths at each 1 million year time step through time, and then we measured the length of subduction zones in total. Then we characterized them as being either interoceanic subduction zone, interoceanic arcs or continental arcs based on their proximity to continental polygons. So you can see the yellow line shows that that section of subduction zone would be classified as a continental arc, and the blue would be an interoceanic arc. We used a basic search mechanism to be able to figure that out. We also measured, in a similar way, we measured the intersection of subduction zones with carbon platforms, which are the green like polygons that you see there. These are some of the results that we got. So here we have subduction zone lengths. Oh, there's a pointer. Oh no, I don't know how to use it. Oh yeah, there we go. So we have subduction zone lengths in red. We have proxy data in blue here and here. This was a smoothed proxy data curve based on 490 proxy records, and this one is an updated and expanded version in 2011. So you can see that, about like from 400 to 300 million years, the subduction zone lengths are quite variable. You have an enormous length in subduction zones at about 200. I know you can't really see that, I'm sorry. It's about 280, 260 MA. Maybe that can be explained by subduction zones developing when the Turkey's Ocean began to form. Around 200 MA, that was the breakup of Pangaea, so you get like quite a large increase in subduction zone lengths there, and it kind of is followed by the lag effect in the atmospheric carbon dioxide response. So there are 3 parallel peaks of carbon dioxide and subduction zone lengths in the Cretaceous. One at about 80 million years, one at about 55, and one at about 40 million years. So the 55 million year peak coincides with the Eocene climatic optimum, and it could maybe easily be explained by the collision of India and the Eurasian continent, which formed the Himalayas. There are a lot of feedbacks in there that we, climate is obviously very complicated, but these are some possible tectonic explanations. So the present day lengths of subduction zones at about here that we calculated were 61,000 kilometers, which is, vastly bigger than, it surpasses the other estimates by around about 10,000 kilometers. So, Shellart and others found it was like 48,000 kilometers. Generally, people seem to write about subduction zone lengths presently being 55 kilometers. So yeah, ours is quite a lot larger than that. But I don't think any of these estimates have been attained using a plate kinematic framework. So bear that in mind. They usually use I think at least Vandermeer used the geologic maps and measured it that way. So here we have in green the carbonate platform lengths, the intersection of volcanic arcs with carbonate platforms. This is that first model where you just have active carbonate development and carbonates being depleted. And this is the accumulated model. Again, the red is the subduction zone lengths, and the blue are the proxy data. So on the left, so from about 400 to 260 million years, you don't really get much interaction in both models. But then, maybe this is due to patchy reef development, I'm not too sure. During the Cretaceous, so I've highlighted it here, after about 120, 130 MA, the first model shows an increase, a dramatic increase in the amount of carbonates intersecting with continental arcs. And the right-hand side doesn't really show that as dramatically, but it does show that there's an increasing upward trend of interaction. So the second model would suggest that as crustal reservoirs grow, there will be more climate-driving potential of continental arcs, and you don't really see that here because you see like a divergence of, the atmospheric carbon dioxide and then the interaction with carbonate platforms. But it could be because there's a number of factors that are involved in driving climate. The mechanisms still aren't fully understood. But I guess the takeaway is that the profound release of carbon dioxide from the decarbonation of crustal carbonates during the Cretaceous and the early Paleogene was quite high, judging by these models. So generally, the continental arc regime seems to have switched at about 250 million years. And, this is the proportion of volcanic arcs that are continental arcs. Sorry that the font is so small, but like this is 100%, this is 40%. So it was about like less than 60% before 250 million years, and then it is about 65 to 85% after that, from 250 million years ago to present day. And I think the change here was because of the way we constructed the models. They were like stitched together at 250 million years. So, the giant dramatic jump there is probably because of that. So you also see that during the Cretaceous, there are some peaks that correlate really well with atmospheric CO2. There's like a peak here, which maybe could explain this. This shape here is like kind of mirrored. You also see that, when the continental arc regime transformed into a predominantly island arc regime around 50 million year, there is like a slight average drop in the proportion of continental arcs. But, like overall, it's not very dramatic, I think. But after this time, widespread interoceanic arcs dominated because of the creation of the Pacific Ocean. So that could have been producing less CO2 emissions as well, because the island arc regime dominated. In any case, we did find much larger estimates for the proportion of continental arcs than other estimates. So at present day, our model showed that 71% of all volcanic arcs are continental in character. But, others have estimated far less than that, about 30%. So, that's something we really need to test to see if that's, if that's the reality. So these are some of our conclusions. The increases in atmospheric CO2 during the continental breakup is supported by the dramatic increase in subduction zone lengths, which is a surrogate for arc volcanism in our model. So the greater lengths of continental arcs, especially if they intersect with carbonates, may be the single largest explanation for increased global production of carbon dioxide during the Cretaceous. You can see that through the correlations that you see here, perhaps. Yeah. So previous studies have suggested that the subduction zone, that continental arcs were about 200% longer in the Cretaceous and the Paleogene compared to the present. So that would match the carbon dioxide levels of 4 to 8 times higher than in the present. But our results don't really show such a high comparison, so that's interesting to note. Also, we found that the length of the global chains of continent arcs were more likely to interact with metacrustal carbonates from 250 million years, but again, that could have just been an artifact of how the model is stitched together. So what are some of the outcomes of the project? And this is, some of the work we've been doing most recently. So after we created a visual model that represented subduction zone flux through time from a plate tectonic and in a deep time perspective, we were able to create a lot of outreach material, including some animations. We created a blog that was able to give tutorials for people to be able to use the workflows that we created themselves. And yeah, we're sharing all our workflows openly through the DCO data portal, which is like the picture in the middle, the upper one. So yeah, this enables people to be able to take the workflows and use them themselves, test their own hypotheses. We have tutorials to be able to explain how to use them, and so hopefully, yeah, this will help with the proliferation of people interested in deep carbon science. Our models satisfied the short-term goals of the DCO, which was to create first approximations of data. They're by no means perfect, but it's the first time really people have been able to visualize how subduction zones have evolved. For the past 400 million years, we don't really have that kind of data available to us because it was lacking previously. Then we tried to communicate it as best we could, and we really think that the deep science researchers and community do stand to benefit from being able to use the community structure of G-plates and our subduction zone analysis to be able to use in further deep carbon science applications. But that's about all. Any questions? Yeah.
So I do have a question. It relates to the length of subduction zones, and I guess this might be a discussion point, but one of the ways to increase the length of subduction zones is to increase the curvature, right, and have a lot of oblique subduction. So and I can see that would have an effect if you're worried about how much material is going down. It might. So some pieces of this, one of these boxes, I think, might be dependent on the sort of the projection, the plate vector of the subduction zone, and the other stuff might be purely related to the length of the subduction zone. So I'm curious about that whole obliquity question.
I'm going to let you two answer this one.
Well, that's right. The problem is that from the geological record, we can usually tell where there was a subduction zone, especially a continental one, from rocks that have been preserved. And of course, it's much harder to tell exactly what the geometry of that subduction zone was. And for times before the Cretaceous period, say, it becomes very hard to actually reconstruct even a crude model for the places that occupied ocean basins that now no longer exist, right? And of course, it depends on the behavior of those plates, how oblique the subduction might have been in different places, and how subduction zone curvature might have evolved, and so. So this is I guess this is going to be a topic for discussion, right? How to do this better. So one way forward, that I can see is as we go into deeper time and we have some idea, perhaps a rough idea of where the subduction zones and where mid-ocean ridge systems were. Right? So then what we actually need is a forward geodynamic modeling approach to then use our knowledge of plate driving forces, right, to create models for how those synthetic plates might have moved through time. Right? So this has sort of been the goal in the back of our heads for years, right? But we haven't really managed to get there. Right? And so this could be even a relatively simple model, right? That considers slab, pull slab, suction, and ridge push. And so let's say, okay, let's say we have this geometry of plates, and this is where we think our subduction zones were, and this is where the mid-ocean ridges were. Well, how would we expect these plates to move, right? And where would subduction then, as a consequence, then have been more oblique, and how do we expect subduction curvature to evolve, right? So I think that this is actually a really important point that you've raised, that will require collaboration between geodynamicists and plate kinetics of people to resolve.
Can I just add a couple of comments as well? So in our models, the subduction zone geometries are static. They don't deform themselves. And they just move around based on the motion of the overriding plate. But we measure the lengths on a sphere. So the the problem of projections shouldn't be too much. The problem is really how true, how close to reality are plate reconstructions back in time. And you saw that, like, with years of modification and updating, say, the Tethyan region, Southeast Asia, we added more and more subduction zones. One thing that might help is when we actually start looking at the slab flux, which is a function of the convergence rate at different parts of those subduction zones.
So I think that's what I mean. When I meant projection, I just meant that if you've got something at a very steep angle,
exactly,
then the projection of this vector is a small one. So it is about the subduction flux.
Yeah.
That was really the basis of the question.
And so we'll look into that in terms of, along each subduction zone through time, figuring out the normal component of that convergence.
Yeah. Great.
That was great, Jody. Thanks. Have you looked at something like seismic database or compilation thereof, like slab 1.0, to try and have an idea, feel for what might be the correct? You say you have 20% essentially difference between what comes out of the plate reconstruction and what comes out of independent estimates for present day subduction zone length, and that seems like a fair bit. So in the model, in what you're looking at the reconstruction, and what's important, I suppose, is the trend for time, more than the absolute numbers. But at the end of the day, if you want an absolute number, it's important to have an idea of present day subduction zone length.
Yes.
So that 62 versus 42 seems quite important to me.
Yeah.
And then the second or related, and that's a kind of worms, right? I'll just put it out there. That these are not nice graphs, but what kind of error bar should we have around that orange line, and should it increase back in time?
Yeah, I agree. I'm not quite sure how we would construct error bars, but I agree there needs to be some kind of maybe if we could combine both models of the way carbonates have interacted with time to be able to create like a minimum amount that they interact and a maximum amount, that would be a lot more accurate. I agree. I think that they do need to have error bars.
I think just simply even classifying subduction zone geometries in the past as being purely synthetic, required by the kinematics, or subduction zones that are supported by the geological record, that will help.
But often also it might be part of the subduction zone. There's an arc, the arc is so long, and then there's an inference, and that's the best we can do in the global plate reconstruction. That from that arc that's been documented over a few hundred kilometers, say, or something like that, or a few outcrops, then we end up with a subduction zone that's a few thousand kilometers long.
Mm-hmm.
And so that's the difficulty here, and seeing how in the Paleozoic, the amount, so many of these Paleozoic subduction zones will be infraoceanic, they will be entirely synthetic. If someone believes an ocean dynamic is, so it formed in a different way, what's the effect? How much? Maybe putting error bars is too difficult, having really n numbers.
Exactly.
Just shutting off a whole system of subduction zones and saying, from that Paleozoic reconstruction, this shouldn't be here. What would be the effect?
Well, it would require us using different models of different plate kinematic models, which is entirely possible as well. Like the tool we've used, we applied it to the Matthews current plate model, but you can use that for any, as long as you have the rotations and geometries, you can use it for any model you have. So that would be one way to be able to create different end members, right? You have different theories, have different models, you create different end members, but this is the one that, we created with ours. I do agree that it would be great to have more end members based on, parameterization, changing things slightly. And I think that's one way we can go forward with this, because it's,
Not suggesting you should close topologies and do, because a lot of man hours go into each of these full descriptions of the kinematics. But maybe just having even a way of saying, okay, in this reconstruction, so much is synthetic. You should take all the synthetic subduction zones out, what's left?
Yeah.
That's a good point.
large discrepancy in the length of continental arcs.
Yes.
So that was greater in yours, 71% compared to 30%. It's a huge difference. And that's very important in your model. Why do you think that difference is so great? Are you defining continental arcs differently in some way?
That's a really good question. Maybe it is because we are defining it just by the fact that they are intersecting with the continent-ocean boundary. So we have masks of the continent-ocean boundary. I'll see if I can get a photo. So everything that intersects here would be classified as a continental arc, which is a very it's an overestimate, I think. It's basically saying that there are volcanoes here that are continental, and in this example, it's clearly not the case. So it is a problem that they are they're disparate, and I think it is because it's overestimated. And I think that's something we should take on in the future when we're classifying that, because we ended up getting very different results to past.
So how did other people classify what was continental?
I think Vandermeer and colleagues, the way they did it was by looking at a geological map and just being able to maybe digitize that, but just looking at static maps and measuring it from what they know.
Can I just make a comment there? Our plate boundaries at present day are the same ones as those from Peter Bird. So I'm not really sure why there's such a huge discrepancy, because he did a huge synthesis of plate boundaries at present day.
Interesting, because the length of subduction zones at present day is 52,000 kilometers based on Bird. I think I didn't write that in there, but it is.
Yeah. So in his synthesis, there are parts even in Southeast Asia, I had to add additional subduction zones. He did a global synthesis. There are things that were missing. So some of the other ones may have been more schematic. With the Vandermeer one, they largely use seismic tomography, from what I understand, and so I don't think that it's easy to differentiate between continental or interoceanic subduction from their method. So I think there's a little bit of confusion.
Yeah, I'm wondering whether there's a difference between what you call continental and somebody else might call mature arc. So, are there just ways that they've classified that crust differently to get something that's as big a difference in those models?
So I'm actually looking at the map from the So first they don't really give a proper reference. They say it's taken from GeoMapper, which is an online tool where you can quickly grab certain types of data, and I can see that their definition of continental arc is extremely conservative. And even the location of subduction zones is not very complete. But this is a point that probably needs to pay a little more attention to showing these maps at present day. Where are subduction zones, continental, interoceanic versus theirs, and why does the difference arise?
Sure. I'll bring that into my presentation tomorrow.
Yes. Because as Nico says, we're starting at the present day, so there's a huge discrepancy that we're unsure how it came about, and it becomes less robust than what it was.
Yeah. Well, maybe the reason why they're so different is because the Vandermeer paper was an extreme underestimate, and ours is maybe an overestimate as well. So then you just have the two different ones. But anyway, I'll bring it into my presentation tomorrow.
That was really excellent. Thank you. I wasn't 100% sure how you were using the Kiesling database, that 400 million year record. So you took that and then you digitized the approximate locations of the platforms at each of the time steps.
Yes.
And then move things around.
Essentially, yeah. So Kiesling had figures like this.
Yeah.
He also had a bunch of shape files which were the exact same thing, but they weren't georeferenced. So just we had to do that ourselves, and they were for different periods. So I think the late Cretaceous, we were able to define that as being around like 65 to 90 million years, and then dominated through a different time period.
Right.
And so we digitized that, and then we said that they existed for the periods that corresponded to Kiesling's paper. Does that make it more clear? And then that's how we were able to make. That's how we're able to. Yeah, and then we gave them an ID so that they were moved with the plate they were on top of, and then they were able to move dynamically.
Right.
With the plate model. Yeah, but it was from static figures.
And they were only active carbonate platforms that he plotted or interpreted. Like we discussed, there may have been inactive, buried carbonate
Right.
platforms.
Okay, so that was the sort of accumulation model.
Yeah.
And then, so this is the accumulation one, and then when that ends, the active one should start. Yeah, which is where this is what Kiesling had. He had them changing it each time step, which were the ones that were active at that certain period of time. Oh no, it's stopped.
So, Jody, this is along the same line. So say, if on the left-hand side, following the hypothesis that the decarbonation process is very effective, right? So then very old carbonate platforms, that have, at least those that have been adjacent to subduction zones for long periods of time, they should be quite depleted of carbon relative to young ones, right? So that's something that one should be able to test, right? There must be published information, about the total carbon content, of old versus young carbonates, I suppose.
I suppose. I'm not quite sure how they would do that. How they would know how thick the carbon reservoir is beneath, for instance, Mount Etna.
Yeah, it would be based on scratching the surface, I guess, depending on looking at rocks that are accessible. At the surface, close to the surface of the thick carbonate platforms, and having a look.
Comparing carbonates that have been magmatically altered to ones that are further away.
Also comparing it to carbonate platforms that have never been close to subduction zones that would then be more intact, presumably, in terms of the carbon content.
Yeah, well, there are just a bunch of other parameters as well that influence the decarbonation process, like how steep the geotherm is. That's just one of them. There's a bunch of other things like how deep they are, how big they are. But yeah, it would be good to look through the research that's been done and get some better estimates, like how they've evolved through time, or how they've been depleted. Time for a break.
It's it's a coffee break now.
There you go. Thank you, Jody.
Thanks, Jody.